Okay, so here we're going to take a look at functions, in particular this idea of an injective function. So here we're going to define, first of all, an injective function. So we say f from A to B, right? From set A to set B is what's called injective, right? And this is what we call 1 to 1, provided every element in B is the image of at most one element in A. All right, so so first let's take a look at here what this means. So here let's take a look abstractly if we were to write like the set A consisted of A, B, C, D, and the set B consisted of the numbers 1, 2, 3, 4. All right, so here would be an example of something that is injective, right? Every element in B. So here we're looking at the codomain, right? Is the image of at most one element, right? So keep, again, language important here, how we word this, right? At most, right? So here, at most one, so it could be 0, right? So just keep that in mind. Let's say if the set A, B here was 1, 2, 3, 4, right? So here, this would also be injective, right? Because here, each element is at most 1, with 4 being 0, which still satisfies the above condition. All right. Now, the main difference here is the example of our first function is this notion of onto, right? Where not only is it 1 to 1, but every single element in B has an image exactly once, right? So different types of injective functions here, right? Both injective. Right now, what would not be injective, so here, injective, right? If we had, let's say, A, B, C, D, right? 1, 2, 3, 4, right? So if you had something like this, right? So this is not injective. Because we see here the image 3 has 2 elements in A. Is a function, right? But it is not injective. All right, now, in terms of the size of the sets, right? Because that would play a part in this, right? If the size of set A is bigger than the size of set B, then F is not injective. All right. Okay, so think, for example, here, this idea here, F A onto B, right? So the function that maps the set A, which is, here, let's define this formally. Set A is the students in the class, in a class. And then B is the months in a year. And we could say F is the function that maps students to their birth month. Right, so let's say we have, in this example, that we have a class of 25 students, right? And B is fixed, right? B is always 12 months. Okay, so here we could see that there is no way that F from A to B can be injective, right? Because if we have 25 students, right, and 12 months, then most definitely a month will have more than one student. Okay, there will be at least one. All right. Again, this is this idea here of this cardinality, the size of a set. Right. It's almost the same principle as the pigeonhole principle. Right, where you can think of the set B, the codomain, to be the holes, right? The containers, right? The objects that hold things, and then the set A to be the objects that go into those containers. Okay, so we could see here a function defined in this manner will not be injective. I don't even need to know everybody's birthday month. I know for a fact that they will not be injective, right? That in fact, I'm guaranteed at least there will be 1 month where at least 3 students will share the same birth month, right? Okay, right, and that's also kind of based off of that pigeonhole principle type thing, and the same if the cardinality of A is bigger than the cardinality of B. All right, moving on here. So another thing about functions and their sets, their images, and then their elements in the domain. So let's say we have a function here from set x to set y, right? Let be a function. And let's state even further, we'll let A and B be subsets of A. So excuse me, subsets of X. If A is a subset of B, then f of A is a subset of f of B. All right, so the images of A are a subset of the images of B, if we know that A is a subset of B. All right, so let's do an example here where we apply this property here of functions. Okay, so for this example here, let's let f be a function from x to y, and let A and B be subsets of x. All right. Okay, so here we have A is a subset of x and B is a subset of x. Okay, I want to prove that f of A intersection of B is a subset of FA intersection with FB. Okay, all right. So let's start here. So with this factor, right? So we'll let image Y be an element of f of A intersection of B. Okay, so by definition, there exists an X element of A intersection of B such that f of x is equal to y. Right? Now, since x is an element of A intersection of B, again, this means that x is an element of A and x is an element of B. Well, if x is an element of A, then by definition y equals to f of x must be an element of f of A, right? The image of A. Right, but also x is an element of B. Since since it is in the intersection. Right, so that means y equals to f of x, but f of x is an element of the images of b. Okay, so now individually, this y is an element of f of a and f of b. So we have shown here that a intersection of b is a subset of the images of f intersection with the images of b, because y was just a general image in f of a intersection of b.